Welcome back. So now we have our speaker, Professor Amit Apte. He is a professor at IISr Pune, Department of Data Science, and he will be talking about dynamical and statistical model of Indian monsoon rainfall. So yeah, over to you, Professor.
Thanks a lot. Okay, thanks to Vishu and all the organizers for giving me an opportunity to talk about a topic about which I know very little. So I learned a lot in the last week. Unfortunately, I couldn't be here the week before. I would have loved to. I listened to the pedagogical lectures and they were very useful to me. So thanks. And I guess I have no idea why this quote is here. So hopefully, you didn't have to. Okay, so I will talk about a very, I guess, specific system. So this is not a very general talk. It's about a very specific topic, which is the Indian monsoon. That's one of the topics that Tim Lenton mentioned yesterday. And I guess my point would be to try to convey the difficulties in addressing the questions related to Indian monsoon and show some non-results and leave with some questions. The model that we have is really, the reason I said non-results is because the model that we have doesn't really answer the kind of question that we would like to try to answer, which is what Tim also mentioned, that it's still a topic on which there is a lot of debate because the models are not such well developed yet. And hopefully I will convey that. So, okay, here is roughly, I will start by describing what a monsoon is, maybe talk a bit about the kind of data set that we use and the model that we are trying to develop. And if I get time, I don't know if I will get there or not, a statistical model or statistical methodology. I guess it's not a one single model as such, but of how to deal with these kind of data sets. So, okay, so starting with this, maybe I should switch to, so what exactly is monsoon? It's just actually variation of winds. That's how the term was coined. It's related to the winds. It was coined basically by sailors. It comes from Mosam and so on. Okay, so there is a etymology that you can read about. And this can be now very easily seen instead of showing plots of static plots like this. So on the left, it shows, so to say, the winds in wind. You can't really see the winds per se. Yeah, no. Okay, so a better visualization is here. So this is just earth.null school. There is windy.com these days, and there are quite a few such beautiful visualization tools available now. And so this is a randomly chosen day, the last day of January, not so random, and the winds for that specific day of 2022. So it's not an average picture, but the average doesn't look terribly different from this. The details of some convergence happening here and so on and so forth will be different, but these are the typical winds in that direction, right? So you can see that the winds are coming from the Indian landmass towards the Indian Ocean side, and you can imagine that do not cause the rain. There is no moisture here. Oh, by the way, the shading is what is called total precipitable water. Think of it as essentially humidity in some appropriate measure. Okay, so that's January. And if we switch to June, it didn't switch. What happened? Oh, okay, took some time. So this is June 30th of the same year. And again, the average picture is slightly more smoothened out and so on, but the general thing remains the same. There is lots of details here. Of course, there are hurricanes, and, well, maybe not hurricanes, but typhoons in this part. And but the point is, now the winds are coming from the ocean side towards the Indian subcontinent, and that is what essentially causes the largest amount of rainfall during the monsoon season. And this could be shown for, say, July, August, September, and so on. Right? Okay, so let me go back to the slides now. So it's periodic variation of wind, and I just showed for one specific month or day. So on, if you look at winds over winter months, summer months, and so on, this variation of winds is very clearly seen in the. Of course, the way we think of monsoon is, okay, it starts raining and it stops raining, at least some part of India. If you're in Chennai, then that doesn't quite happen. But average over the Indian region, this is from the data set only over the Indian political landmass as of now. But anyway, that's because of availability of data set. Anyway, so what this shows is what we already know very well. June, July, August, September are the monsoon months, the rest are not. And but monsoon really relates to much larger thing than just rainfall. It really relates to wind. But they are quite reliable in the following sense, that if you look at the onset date of monsoon, it doesn't vary a lot. It's about plus minus 7 days. In fact, the standard deviation is 7 days for the onset date over last 150 something years. And that's also partly because earlier the data sets were not so robust and so on. So maybe if we go back and recalculate the onset dates and so on, this could be even reduced to further smaller. So you can see that the uncertainty on onset dates is much less now because we have availability of data sets. And okay, so it's quite reliable in this sense that it comes periodically and with not too much variation with that. Also, the long-term mean is quite robust. So the variations on top of the long-term mean, which is about 850 millimeters during the 4 months, June, July, August, September, is just about 10%, roughly, which is not a large variation, right? I mean, thinking of the kind of systems that Sujit was talking about, 10% variation is what you would like to stay far away from. And so, but this is a natural system, so we can't play around with it, luckily, yet. And so this is the variation, but then this has a huge effect. So less than 90% is what is declared as drought. More than 110% of the long-term average is what is declared as excess, and then yeah. So they're so quite reliable in the sense of the total amount and the timing and the periodicity. What exactly is the difficulty? So I guess one thing I would like to try to convey is that it is a complex system for various reasons. And luckily, I didn't really even have to type the slide. A wise lady yesterday said everything about complex system I could have said. And all of these apply to monsoon as well, word to word, literally. Local interactions, of course, fluid dynamics, these are all fluid systems, these are all local. But the local interactions between individual components are not quite what describe the system, right? System behavior. So I could have crossed out the ecosystem here and put monsoon, and it will still be the same. They cannot be understood by just individual components. There are feedbacks, and I'll come back to the point of feedbacks later. And that's essentially one of the key points about why these systems become complicated. Feedbacks, amplification of minor variation in initial condition. I guess that's kind of the definition of chaos. I'm not sure if chaos is necessary for this, but anyway, it's not clear whether monsoon system in any sense is chaotic or not, but anyway. And there are emergent patterns clearly, right? So all of these things actually are present in monsoon. So in what way are they, is the monsoon a complex system? Okay. So let's discuss a bit about that. So I showed you a very average picture, but there's a huge geographical variation. So if you have traveled around India during monsoon season, you will know this. And this shows rainfall over the 4 months across this region. And the darkest regions are something like 80 inches. Sorry, I got this from, oh, wait, what happened? Okay. So the URL is missing where I got this from. Anyway, so it's in inches, sorry. Inches to millimeter conversion would have been easier to do. So this is about 80 inches, and the smallest amounts are about 10 inches per year. So which is huge variation across different parts of India. And this typically is called a monsoon zone, where you see somewhere average in between the two extremes that you get here. And so this is one part of the complexity. Large amount of spatial variation, and okay, I guess this was another way to look at it. If you and the geographic variation is not just, so I guess what I showed showed was using data sets from the land measuring stations and so on. But this is not just a system sitting on land. It's a spatially extended system over the oceans as well. And this is one way to see it. So this is January, February, March, so on and so forth. So June, July, August, September, rainfall over a region that includes the Indian subcontinent, but also includes the Indian Ocean. So I guess the variation is so large that any kind of uniform color bar doesn't capture this very well. Maybe you can do a transform, which is what I did. So if you take, I don't know, so don't ask me how high this, but anyway, a tan hyperbolic of the monthly mean rainfall divided by 50. It somehow just makes the picture look good. So the variations can be seen much more clearly. That's all I have no other motivation for doing this. But anyway, now you can see the variation much more clearly. And there are lots of patterns here. So for example, over the Indian subcontinent, there is a lot of rainfall during these 4 months, which is what I explained earlier. But the rainfall over the equatorial region pretty much continues throughout the year. Well, except during the May, somehow it's just a bit less, but anyway. So during these months, there are 2 rainfall zones, so to say. One is over the Indian subcontinent and the one over the equator, or a little bit south of equator, continues to be present. And I guess I didn't say much about this, but so there's large geographical variation, which probably has something to say about.
A quick clarification, when you say Indian monsoon, it includes that equatorial region as well, the rainfall over that?
The equatorial region is not a monsoon zone.
Oh, okay, it's always there.
See, the rainfall or the wind variation across the equator is not as dramatic as over the Indian subcontinent. So the monsoon zone is really just over this region.
Okay.
That part is not part of the monsoon zone per se.
Okay.
This is just for comparative.
It would be coupled in some way, clearly.
Oh, it's very closely coupled. Yes, it is there's no way to separate the dynamics. Okay, actually, I will do that later. So failed to do it well, but anyway, to try to capture the dynamics in this region all by itself. But it's not a very successful exercise. So yeah, it is coupled, and this is not monsoon, because if I plot, actually I have just one next slide, I think, or maybe 2 slides. So let me come to that one now, since you asked the question. This is 21-year average rainfall shown in blue. And if you do multiple different averages, say 10-day or 10-day and 5-day, I forget how many days average I did, but anyway, 5 days or 10 days running average, then you get this green and orange kind of curve, so slightly smoothened out. 4 different locations around the map which I showed earlier, the same region. But if you look at any individual year, so here I have plotted all the 21 years in 21 different colors. One of the years is black, just to highlight one single year. So you can see that if you look at this map, this doesn't look like this nice smooth curve of small rainfall. It goes up, then falls down, and then flattens out, right? Any given, we know that also. It rains for 10 days or maybe 3 days, and then stops for 10 days, nothing happens, and then so on and so forth. That's what you see for any individual year. Once you average out over, say, 21 or 100 years, then this kind of nice smooth behavior comes out generally. So the quiz is, which of these is in the monsoon zone? So clearly this has a very different behavior than this and that and so on. So the behavior across these different spatial regions is quite distinct. In fact, this is probably close to Chennai, that's my guess anyway. So the answer is over here. That one, L1, this was the core monsoon zone, as we can expect. Nothing much up to May, picks up in June, July, August, September, then again goes away. L2 is somewhere, I guess the difference is the amount of rainfall, which you can't see now here. But anyway, this rainfall is much higher than that. The peaks are much higher, as I showed in the Western Ghats, along the Northeast and so on. And this is the Northeast, and this is near Chennai. I didn't show, oh, sorry, I forgot to include sorry for including the wrong figure. There was one figure with 5. There was one here, which is kind of flat. It just shows rainfall all throughout the year and no monsoon per se, no monsoon signal. Okay, so that's partly to answer your question. This is a missing figure. So that's the, and by the way, this is any given day. this is what it looks like. Right? This nice smooth variation of high rainfall here, high rainfall there, and so on and so forth. That's completely different on any given day. It might be extremely heavy rainfall in some locations, just around nearby, maybe not too much, and so on. And so if you smooth out over time and space, the behavior is very, very different than what actually happens. And yeah, so this I basically said already, which is if you look at any given year, it rains a lot, then stops, then rains, and so on. Okay, so there is large intraseasonal temporal variation. So spatial variation, temporal variation, both are significant. That's one of the reasons why this is a complex system. So just to quickly summarize, we saw that the interannual variability is small, but has impact in terms of droughts and excess rain and so on and so forth. All of this is related to the ocean dynamics, which I didn't talk about at all, but in fact, it's related to ENSO, which is mostly the Pacific Ocean phenomena. It's related to Atlantic Ocean. This is Atlantic Meridional Oscillation, AMO. And there is a relation between Atlantic Ocean and the monsoon. Of course, it is highly related to what is called Indian Ocean dipole. And I didn't talk about these at all, just stating it as facts for now. It has a complex spatiotemporal variation, even within a season and across different years. The physical mechanisms that go behind it are equally complex. So there is basically heating and convection. Tim yesterday showed this very broad plot of the moisture coming from the ocean, convection happening over the land, causing clouds and rain, and then this whole cycle and so on. So this kind of cycle plays a very important role in understanding this variability. And unfortunately, because convection is a huge unknown in some sense in capturing it well in large models, in general circulation models, these kind of very large Earth system models do not capture the interannual or the intraseasonal variability of monsoon very well. And I've not really talked about that, but that's something that people are struggling with in large-scale climate models even. Okay, so what I will, I guess, talk about is try to come up with a smaller, simpler model. I'm calling it physics-based. Maybe that's not a good word, but anyway. And hopefully maybe some statistical models if I get some time. Okay. Yeah. So again, yesterday's talk was a nice introduction to what I'm just about to say, which is that, so Tim talked about why, or rather he mentioned that monsoon is not quite included in the list of tipping points, largely because it's quite unclear. Yeah, this is, I can't say it better than this. One of the key criteria for tipping points, I guess that's a very nice summary of this whole last 2 weeks, of what is required in a system for tipping point, as he captured quite well, is important feedback within the system that is so strong that it can become self-propelling. And this is a key characteristic of systems that have tipping points. And in the case of Indian summer monsoon, there is not enough evidence on the tipping points essentially because the debate about whether such a feedback and such a fundamental tipping point exists in monsoon is really not settled. And that's basically why he showed this picture. There was this paper in 2005 which argued that maybe there is actually a tipping point, but then later papers not. And in particular, around the same time as this that he talked about, Boos and collaborators of paper, there was a paper by Ashwin Sheshadri, who is in COS in IISc, about arguing why the arguments given here are incomplete, and if you include the additional feedback mechanisms, then using the appropriate energetic arguments, the tipping point does not appear anymore in almost identical model to what was used in this paper. So slight changes, it's arguable about what you want to leave and what you want to keep in a model, and slight changes in what you include cause very different conclusions in terms of whether a tipping point exists or not exists and so on. So a good understanding of such kind of phenomena require. So I guess one thing that he didn't talk about is that I think is necessary is all of this understanding largely comes from having useful and representative models of the system. Purely based on data sets, getting all of this information out of whether there is a sufficient appropriate feedback mechanism that can lead to tipping or not is kind of hard, and especially hard for such large spatio-temporally varying system. And this is thousands of kilometers with variations across the space which are of the order of tens of kilometers and so on. So it is just purely data-based understanding of these feedback mechanisms is still far, far from what we can do. And so we need good models. And that's the basic attempt which I will try to present about. And this is based on the work of Ziegfeld that he mentioned yesterday as well. Okay, so I will skip this. Okay, so general methodology about what type of modeling we would like to do, but I'll skip this. Sorry, I guess I'm kind of running out of time. But so essentially, it's a model that the crux of the last two slides was that developing models based on first principles, in the sense of try to understand the physics of the system, fluid dynamics, thermodynamics, and all of that, and put it all together really does not work very well for this system because of the complexity. And what we need is more phenomenological aspects and try to understand relations between different variables using the data sets and then put them in a dynamical model, which is the focus here. So we would think of the Indian subcontinent as a box. And in that box, try to understand the fluxes of energy and moisture. Of course, they are driven by winds, but the winds themselves are coupled to these energy and moisture fluxes. And that's the dynamics that we would like to capture in a simplified model. And what do I mean by simplified? Of course, this is exactly what the partial differential equation based climate or weather models do, but they're just too complex to try to understand these kind of feedback mechanisms. So we would like to develop a ODE based model, which is what Ziegfeld did in her thesis in 2003 and developed. But again, I'll show what the complexities are, why this model has limited utility even until now. Okay, so not to mention the fact that not too many people have worked on it. Literally, countably on my fingers, few number of papers in the last about what, 20 odd years. Okay, so the idea of the model is to, as I said, put a box around it, try to capture the dynamics of just these three aspects: energy, humidity, and rainfall. Of course, that relates to the groundwater. And there was a prior model that was for African summer monsoon, and that was actually quite more successful than this one. So yeah, I mean, that probably is partially the reason why African summer monsoon is more, the tipping point aspects of African summer monsoon are better understood than that of Indian summer monsoon. Okay, so so the box, yeah, right. So this is India now, that box, and as I said, these fluxes is what we will try to capture. And of course, there is the radiation coming in and going out to the space. So the processes is sort of a partial list of processes that possibly are important, and you can already see that it's not such a small list of things that you want to, even things that can be called bare minimum. So condensation clearly is extremely important. That's what the condensation of water vapor into clouds is what causes the latent heat release, which is what drives the whole cycle of convection and so on. In addition, the evaporation from the ground is crucial because the rain falls and then the water evaporates within the same season. That is quite important. And as I said, advection at the boundaries, the flux from the boundary. That's for the water vapor or moisture. For the energy, same process, as I said, the latent heat and the latent heat of evaporation now from the ground. Incoming radiation, clearly, but incoming radiation which is modulated by the cloud albedo. So clouds reflect the radiation. So more the clouds, well, you would expect more rain, but then if they reflect more radiation, you expect less evaporation. So that's a negative feedback. And so it's not clear what happens with that. But so that cloud albedo feedback is very important to capture. And the clouds also modulate the outgoing radiation as well. So, and clearly the advection. And the soil moisture, it depends on the rain, evaporation rate, and things that just go off into rivers and lakes and oceans. So those are the main processes. As you can see, this list is already kind of daunting. And what the starting point was try to get phenomenological models for each of these single processes and put them into a differential equation. Yeah. So maybe I'll skip the details. It's an unfortunate fact that atmosphere has a 3D structure. And we need to capture that 3D structure even if we want a box model, and simplifying assumptions about how the temperature and humidity and so on varies along the vertical have to be made. And these are the kind of assumptions that are made. In particular, the lapse rate is extremely important because basically what happens is, so what is condensation? What are clouds? The moist air starts rising, and as it gets to a certain critical temperature, it will start condensing. It cools down, and the rate at which the atmosphere cools down has important implications for where the clouds form, and then how the clouds form, of course, imply how it rains and so on. So this lapse rate of how the temperature decreases in the vertical width in the atmosphere is an extremely important parameter, one of the most important parameters in this model. Okay, so the equation just looks like this. On the left is effectively derivative of temperature, d by dt of the temperature. But as I said, temperature changes in vertical, so that needs to be captured by using some integral in the vertical, and that's that term. So this is just the rate of change of temperature with time. And essentially the rate of change of temperature is related to the energy, of course. That's why the latent heat, the heat capacity is multiplying this. And so this is all put together is the rate of change of energy is all the processes that I just mentioned, latent heat, advection, incoming radiation, and all this stuff, right? And each of these terms have to be somehow related to the temperature, humidity, and groundwater. That's the modeling exercise that needs to be carried out. Okay, the humidity is the same thing. The d by dt of total amount of water contained in the water column, the rate of change of mass of water is how much water comes in and how much water goes out. That's all. Okay, but as I said, this is just a placeholder for a complex term on the right-hand side. And the same thing for soil moisture, how much comes in because of the rain and how much goes out because of evaporation or runoff into rivers and so on. Okay, so just to this is just all three equations written in one page. They can possibly be written in one page, except that each of these terms are a complex set of equations. So I guess the way to capture each of these, the interdependence of all of these terms onto the fundamental variables that you want to evolve in time, temperature, humidity, and the soil moisture, these three quantities, W, Q, and T, is where things just go out of hand. And maybe what I will do is the following. Let me just go to, now this is doing this quasi-static behavior of not going forward. What happened? It just got stuck completely. Okay. This is not synced at all. Okay. Yeah. Okay. Now it is synced. I see here something completely different from there. Okay. So what happens is the following. Okay, as I said, right, the albedo changes the incoming radiation. The incoming radiation changes the evaporation rate. The evaporation rate in turn changes the amount of water vapor available. That changes the cloud cover and the cloud. So now that's a loop in some sense, right? And each of these relations have to be now codified into phenomenological equations. I got so tired of writing down all these equations and so confused that I started writing. So these are really the equation numbers that we wrote down on pages of papers from Zickfeld's thesis, in fact. And the relations to each other are notified by, if a quantity in equation 26 depends on something in equation 25, then that's arrow. And that's basically the whole diagram of equations that comes out. So I don't want to show you the equations, you can imagine. They do not fit on about 2 or 3 pages. They take about 4 or 5 pages to write down all of them, right? So that's where I said it's kind of, we wanted a simple model that where we can understand what are the feedback mechanisms, what parameters control what type of feedback mechanisms, and what variations will actually be important to understand tipping. This is not it. So, okay. Yeah, I guess maybe just to show one example here, right? How does evaporation depend? How do we relate evaporation to the temperature and humidity? Right? So of course, the evaporation is different for whether the land is vegetated or not. And this is the most zeroth order approximation. Of course, you can go through a whole catalog of different types of vegetations and how evaporation changes, but this is just the zeroth order approximation. Vegetated land and without vegetation, evaporation rates are different. And how does vegetation now depend? But the vegetation depends on the rainfall, clearly, right? That, as we saw in yesterday's talk as well, the dependence of vegetation on precipitation is non-trivial. Question?
May I ask you a quick question?
Sure,
You
course.
say that you link evaporation with temperature. I don't understand what is P is pressure?
No, P is the
Precipitation.
Sorry, P is precipitation.
Yeah.
Yep.
But temperature definitely defines dryness of soil.
So temperature, temperature humidity will be, this is the relation I have not yet shown, right? So temperature humidity, that will be related to cloud cover, and the clouds will be related to precipitation.
But if temperature is high, even in wet season, ground would be drier, wouldn't it?
Yeah, so this is one of the key difficulties in this model, is that the time scales of these processes are very, very different. And that's not well captured in this model.
Thank you.
Yeah, so this is one of the drawbacks of this model. Yeah. And so there are several places where there are phenomenological assumptions which need to be questioned and examined, and whether they are actually useful or not. And okay. So that's why this hasn't come to a stage where it is like a minimal but still useful model that can be used to understand the behavior of monsoon as a function of various parameters that relate to climate change eventually. So I don't even want to list the number of parameters here. It's of the order of about 50 or 60. It's too large number of parameters to do anything with at all. Right? There's just no way that. Yeah. Okay, so it captures the broad behavior in some sense, if you can think of this as capturing it well. So in red is the model output using all these parameterizations of these processes, and the black with the error bars is the observed data set of the rainfall over that box region, monthly average rainfall. Okay, so does it capture? Does it not capture? I'm not sure. If I were to ask this question in statistics class, I would say no. This is way outside the error bars, but anyway, the overall pattern looks kind of okay. And but the details are completely off. So here is the example. So if you look at the daily variation does not quite match on the top one. Oh wait, sorry, what happened? I went way off somewhere. Okay, so so if you look at daily variation, I didn't write down which one is observation and which one is model on the plots. Sorry about that. But one color is model, the other color is observations. And the daily variation are not captured. Well, if you average over monthly, so if you average over sufficiently smooth time periods, then kind of it matches in different boxes. So the details are not sufficiently well captured in this model. That's the problem. And here is an example of, so now you just have a box model. So you can do lots of experiments, at least numerically. So you can put a box, for example, in different places around the Indian subcontinent, make the box smaller and bigger, and so on and so forth. So this is part of the result that I will be showing. So for example, I still don't know why it actually works well. I don't have an understanding of what's going on. But when we tried to do this using the boundary conditions for a box around the Northeast, it somehow captured the variation reasonably well of the rainfall. It matched the observations not to, it was a fairly reasonable match across the different years. And this is from 2002. So this is about 4 or 5 years of run. And it was okay, but then you somehow just shift the box somewhere else and the match becomes slightly less. You can see that in this region, there are very, very high rainfall events that somehow come out, which is not observed. Question. Yeah.
A quick clarification. So you basically have those 35-ish equations for on a grid, a spatial grid. Is that how the model
No.
is?
So this is not on spatial grid coupled to each other. That's one of the things.
No coupling, but they're independent.
This is just one single box, and on a single box. And all I'm doing is thinking of, let's say, when I say precipitation, that's average precipitation in this box, or temperature, the average temperature in this box.
Okay, and then
they are not coupled across the space at all.
Okay, but what you have is a region-specific parameters. Therefore,
and then the region
capture the.
Actually, not quite. No. So, okay. So what changes is that when you change the box, the boundary conditions will change, and that is region specific. We can try to do the following, which we tried. It just became too computing. That you can try to optimize parameters in order to match the observations as well as you can. But that exercise is kind of, if in the sense, there are firstly lots of parameters. Secondly, what do you want to optimize? Rainfall, multivariate metric, and so on and so forth. It's not very clear as to what is it that this model captures nicely, right? So clearly, this is not going to capture the daily variation of every variable properly. So what is it that you should expect to match well is not completely well understood yet. So that's why, yeah. So I think that's why this parametric optimization is something that we haven't done. The boundary condition change, hence the different boxes change the behavior. Okay, here it becomes much worse. The comparison, even the onset is not properly captured, and so on and so forth. So the same type of box model in different regions works very, very differently. Why? Not very well understood yet. So,
may I ask you a quick question again? Yes. Do you take this box model? I missed it. Did you take orography into consideration? No. So
yeah,
there's mountain there.
There's mountain there. Yeah, well, there's mountain there, is ocean there, and so yes, yeah. So in this case, of course, yeah. So in this specific case, I guess that's. But then, what about this one now? So this one becomes much worse. So it's not. Yeah. Unfortunately, it's not we haven't found a good explanation of what is it that's not causing it properly, and so on. So no mountains. Okay, that's tiny little bit of ocean there, but anyway. And so, yeah. So that's why I said I guess I'm showing non-results. But anyway. Okay, but the point is that the lack of these kind of models is essentially what is the difficulty in understanding the behavior of monsoon properly and relating it to things like tipping points and so on. Because if you don't have good models, and as I said, the data sets are just too complex. I will probably come to that in just a minute, to derive that information about feedbacks and so on purely from data sets. So not having these models is probably the key difficulty in what Tim said yesterday, why this is not included in the set of tipping points and so on. Not well understood, basically. Okay, so Yeah, okay, I'll skip this. It's just showing that over different regions, it's quite different behavior. And we try to understand the processes behind about 10:50. So I'll skip this part. It will go into details of what processes may be contributing and what may not be and so on. So I'll skip this part for now, relating individual outputs of the model to the equations that go into it. Because maybe I will spend a little bit of time on statistical models now. So what's the kind of data set that we have kind of access to, right? One is the one that we have been working with. This is not the only one that's enough, but let's say if you take the rainfall over the region, which is what I was showing earlier, it's available for last about 20, 21 years, 22 years over a resolution of about 0.25 degrees. And so that gives about 32,000 grid points over which rainfall is available every day. And in fact, this is not the most high resolution data set. There are higher resolution data sets available as well. And the kind of, so as I showed you, the pictures that you get are something like this. So very high spatial and also the temporal variability, which I had shown. And that's the kind of data set that we are dealing with. So sorry, I pressed these buttons in the wrong order and then things, okay. Yeah, so, and so this is for over 8,000 days, 32,000 locations, daily rainfall is the data set that we would like to understand. And as was pointed out, part of it is not monsoon. So this is not monsoon zone. Here is Tibet, part of Afghanistan, and so on and so forth. These are not monsoon zones and so on, but they're all part of this data set. So, okay. I guess one of the difficulty with this is what kind of statistical interpretation you would like to attach to these data sets. Basically, to do any statistical inference, you would like to think of what is the data space and what is the sample that you have. And so either you could think of spatial variation, in which case the data set, the data space is of 32K dimensional with a sample size of 8,000. That's one way to think about it. You have daily rainfall, each day is a sample, and the sample space is 32K dimensional. The other way is to think of temporal variation. And in this case, now the data space is 8,000 dimensional, and each location is a sample point. So basically the time series, each time series is a sample at each location. So you have 32,000 sample points. And this is very hard to argue that this is a random sample, because you see, we saw that the spatial variation is humongous. But anyway. Okay, and of course, the other possibility is to just think of it as a spatiotemporal variation with a data space of 8,000 times 32,000 dimensions with only 21 sample points. Now inference become much, much harder. And this is really what we would like to do, right? We don't want to think of each location as a sample or as a sample point, or each day as a sample point, but the spatiotemporal variability is what we want to capture. But the available sample size is just too small for this to do any reasonable sample inference. And that is the main difficulty. This is one of the main difficulties in getting database inferences for this system. Okay, so what I will maybe quickly show, and the reason, talk about the reasons for trying to do this kind of methods is based on the first point. You think of having something like 8,000 samples and trying to capture the spatial variation and understand the spatial variation of this problem. Right? And so I'll skip talking about these two methods, but just talk a bit about the spectral methods that we use, using basically graph Laplacians. And yeah, so the idea of graph Laplacian is essentially based on constructing a graph Laplacian by using adjacency. And adjacency in what sense? So as I said, in this case, we can simply take the adjacency matrix by, it will be 8,000 cross 8,000, by taking distances in the data space. And in the data space, you could either take L2 distance or a L1 distance, and so on. We are just taking L2 for now. So simply measure the differences between rainfalls in the between two sample points and take the square of it. And exponential y, lots of people have done that, that's why. But anyway, no, but there are some nice analytical properties of this using, rather than constructing adjacency matrix purely based on the distance, this exponentiating gives nice analytical properties which may be useful here. Okay, so once we construct the adjacency matrix, the reasons for symmetrizing and normalizing are again because the relation to the analytical properties of these graph Laplacians, and this is quite actually nice for, in particular, spatial processes. So those that have spatial variation. So the idea is that once you construct such a graph Laplacian, which is essentially the adjacency matrix appropriately modified meaning symmetrized, normalized, then the top few eigenvectors hopefully can provide a low dimensional approximation of the data set. That is what is hoped for. And if you have a low dimensional approximation of this, can we now understand this behavior of the monsoon in terms of this low dimensional structure? And I guess this is slightly bit more successful. It turns out that about 30 to 40 modes, which is still not extremely low dimensional, it's still kind of high dimensions, but about 30 or 40 eigenvectors of this Laplacian capture about 95% of the variation in these data sets. And that's reasonable, but still 30 to 40 modes is still quite large, right? Okay. So here is examples of some of these eigenvectors that we see. You can see that they do capture some aspects of what daily rainfall, or what the average rainfall plots look like, say the monthly rainfall and so on and so forth. And essentially the idea is to then project the daily rainfall vectors onto these eigenvectors and use methods like clustering or classification and so on these. That hasn't turned out to be such a big success, unfortunately. So again, in principle, these methods have worked in other contexts where graph Laplacians have been useful. Here it didn't quite turn out to be very useful. So when we did, for example, so let me just go to this plot for now. When we try to do the clustering aspect, which is take the spectral components, spectral eigenvectors, do a clustering, and see what you get out. These are the clusters. So there are 4. So yeah, we have varied the number of clusters. It doesn't really make too much difference. None of the results using 2 or 3 or 4 or 5 clusters do make too much sense, in the sense that it's physically not really realistic that all of these points shown in, say, this faint blue color are the same cluster and have the same temporal variation of rainfall. That is not really the case. And so it's not that somehow this clustering has not given the clustering using the Laplacian eigenvectors does not give results that seem physically meaningful or useful. I don't know. So there's still, but by the way, I guess I'm hiding lots of details which are hopefully important, and hence we can hopefully fix it. But yeah, so that's part of what we have been doing. As I said, the simple but useful ODE model is still elusive. In particular, identifying important parameters in this model. Using these small number of parameters, we can't really do this stability bifurcation analysis in a 60-dimensional parameter space. Not going to be very useful. And in particular, these are really limit cycles. And if we want to include realistic data sets in it, then these kind of ODE models will be non-autonomous. And so understanding tipping points in non-autonomous systems will be a nice mathematical problem to attach to this kind of work. And in terms of the statistical aspects, yeah. So by the way, there is this additional thing that I didn't show much about. Rainfall data set, the one I showed, was something like 25-degree resolution. If you apply exactly identical method but to a 100-kilometer resolution data set, quite distinct results come out. They're not even very, even on a visual comparison, they are not quite comparable. Now that's terrible news. Right? So if the conclusions are kind of changing with changes of data sets or resolution of data set and so on, I don't know, you have to be really, really cautious about this. So, this is very, very tricky in these cases. So understanding the statistical behavior of these data sets is just, and the other thing is we have used rainfall, which is highly discontinuous, as we saw. Using additional variables, say temperature, cloud cover, and so on, which are much more smooth, may have a better statistical stability, but then its relation to rainfall, it's something that's not very clear. So anyway, yeah, there's a whole bunch of stuff. I didn't talk about the PCA, FDA, and so on, so I'll just leave it here for now and take any questions. Yeah.
Thank you. So please, if you have any questions, so please ask. Yeah.
Nice talk. Yeah, so I'm still trying to understand this dynamical box model which you showed.
Me too. Yeah, go ahead.
So within these boxes, there the network that you showed are system of ODs.
No. So okay. So the right-hand side, I just showed like a schematic representation, right?
Right.
It was basically precipitation, evaporation, this and that. What we want to relate it to is the dynamical variables of the OD, which is temperature, humidity, and groundwater.
Okay.
Those phenomenological relations are quite complex in the sense that you say that, okay, let's say that here is the, maybe let me go up to, where was I? Can I click this? I don't know if I can. No, okay, I just have to go through. Okay, so as I said, precipitation will, okay, evaporation will affect clouds. Clouds are dependent on humidity and temperature. Each of these is a relation that somehow obtained phenomenologically, right? Using partially data-based and physics-based argument, some combination of that two. And each of those is written as a equation, which is what I was showing. Right. And so when you write P, the P will be related to clouds. The clouds have to be related to evaporation. That will have to be related to temperature, vegetation, which will, and so on and so forth. Right? So if I just write down each of them as a single equation, then that becomes long, and all of that goes back into the ODE. So if you put it all into one ODE, or three-dimensional ODE, right? It's T, Q, and W, temperature, humidity, and water, the groundwater. For those three ODEs, on the right-hand side, include all of these terms that I didn't even attempt to write down on the slides.
And so within each box, still I see this gradient, right? I mean, so
gradient of that rainfall.
Yeah, when you
yes.
show this map
yes.
of
yeah. And what we are trying to capture is the average over that box. Yes. And whether that's a good idea or not, that yeah. But
so the plot you showed where you have these boxes like in different regions.
So here, let's say this box, right? So this is what is shown here is that the data rainfall. This is the rainfall, the data set.
Oh, that's the data set. Okay.
And so I guess I didn't explain that very well. This is the variation of within that box of the rainfall. If you average over this, what you get is the time series that's shown here.
Okay.
And in this case, I know because in this, yeah, so the blue is the data, yeah, the data set, and the orange is the model output.
And then over space, like when you move the box to a different region, what is changing the parameters?
What will change is, so remember I said there is advection, that is the moisture and energy is coming in and out, going in and out. Because if the wind is coming in, moisture will come in. If the wind is going out, for example, energy will be carried out with the wind. Actually, it's more complex than that. If the temperature outside is larger than the temperature inside, then something else happens. Anyway, so the temperature gradient across the boundary and the winds across the boundary affect the behavior inside the box. But that boundary conditions change in different locations. So the temperature on the western, sorry, I switched this. The temperature on the western edge of this box is clearly going to be different from the temperature on the western edge of this box, and so on and so forth. So the boundary conditions will change as you change this box location at different places, and that will change the behavior inside that box.
Okay, thank you.
Go ahead.
I have two comments. You started discussing whether we have tipping points in monsoon data because it is oscillatory behavior. Have you tried to look at fluctuations with removed long-term seasonal periodicity? Because those may be easier to model. And because if we expect any tipping, like deviation from normal seasonal monsoon, you would probably get signature in fluctuations rather than in raw data. It's my kind of guess, but
Yeah,
maybe it's worth looking into it.
No, we have not tried that, but that's a nice idea. We could, yeah, that. But the immediate thing I can't seem to be able to wrap my head around is how do you create a model for the fluctuations alone without the variability?
Yeah, and it's probably necessary to consider some other approaches.
Yeah, so I think that's something that but anyway, I think it's something that would be nice to think about. Yeah.
And also, I don't know if you're aware, there is a group at Potsdam Institute that work on, they do, I think, stochastic forecasts of monsoons, and
yes,
you maybe can compare their forecasts with your modeled output. And
yeah. So I have seen their work. Yeah. So what they the aim that they had was slightly different, but they also talk in terms of tipping points and critical transitions
signals,
as the transition from non-monsoon to monsoon season. Yeah, so I didn't talk about that. So
they're trying to do operational forecast.
Yeah, exactly. Using So just to mention about this work, the idea of that work is to say that can use dynamical systems ideas to you think of the transition from non-monsoon to monsoon season as itself a critical transition or a tipping point, and then see whether there is a way to try to predict that tipping point. And if that is possible, then that helps you try to predict the onset of the monsoon. And that's sort of the key idea in that work. But yeah.
Please go ahead.
But whether this work of Ziegfeld and Leverman and all that is also from the Potsdam group. So her PhD was from Potsdam, and then yeah.
I don't think the mic is working, so
I think it is working.
It is working.
Just hold it. Yeah.
Hello. Yeah, it's working. So it's not like a question, but more like a curiosity and coming in from his question. So what you have shown is the boxes at different places. I was just curious, what would the correlation between the data and the model output be if I would center the box at one point and change the box size? Because if I change the box size, if I have a small box, the variation over the boundary condition is small.
Yeah.
And if I'm increasing the box size, the variation over the boundary condition is increasing.
Yes.
So I was just curious what the difference between the output and the data would be if I were to do that.
I don't remember the answer. We had tried to do that. I don't remember the answer of what we obtained. One difficult or one difficult in terms of interpretation is as follows. The box model is supposed to capture, so it's average behavior of sufficiently large regions. Taking small boxes is going kind of beyond the validity of the modeling assumption itself in the first place. But as a numerical exercise, that's entirely possible. So we did that, and I don't remember the results of what actually happens. So,
Still
yeah.
considering a region over Northeast, say, and then over the Ghats completely. So still you are varying the size somewhat.
I completely agree. Yeah. But no, we have tried to do this a little bit, but not very systematically, I must say. And I do not remember the conclusion. So, yeah.
Thank you.
So any other question? I have one question. So basically, this system is an environmental system, so its length scale is very, very high. And so how this thermodynamic model will work at that large scale? Because thermodynamics usually works in a very means small scale. So do you have any kind of comments on it?
Okay, large. I don't think the large. Yeah. So the difficulty is as follows: that what we are saying is that over a given box, the temperature is the same. See, if you have a uniform temperature box, then applying the thermodynamics is not a problem. It's perfectly valid assumption.
So basically, each of the box you are
each of the box has no if there is no spatial variation of temperature or humidity in a given box, then the thermodynamic assumption is perfectly valid to use. Right? Not, of course, this is a fluid dynamical system. That assumption is not true. And so in that sense, so not capturing the spatial variation is the main problem. I don't think it's the not applicable. Its applicability of thermodynamics is okay. Essentially, the PD model is a thermodynamic model as well. It captures the spatio-temporal variation of the temperature using effectively thermodynamics. That is, finally, you write down the heat capacity times the temperature variation as the rate of change of energy equated to the spatio-temporal variation of the energy fluxes. And that's, yeah.
Okay. Is there any other question? Okay, so since there are no questions, so let us thank Professor Amit.